This week we want to speak about a successor of the Internet protocol, the protocol IP version 6. And in this first video clip, we want to discuss why it's needed that we have to think about a successor, what's the problem. First to say, IP version 4, the Internet protocol, still currently the most used IP version is and was exceptionally successful. It was exceptionally successful, and for several reasons. So the design of this Internet protocol was so that it was able also to survive changing technologies. So when we see what was the foresight of this basic design of IP version 4, then we see that today it was designed almost 40 years ago, and also today the use is possible. The use of IP version 4 is possible with several new generations of hardware. Please remind that IP version 4 was developed before the spread of local area network technologies. It was designed when networks and when the computers that are interconnected by the IP protocol were magnitudes slower than the computers today. So the IP version 4 works in networks which are order of magnitude faster than those for which IP version 4 originally was designed. And this IP version 4 was so successful since it has coped with huge increase in the global heterogeneous internet. Today we have mobiles, we have sensors connected to the internet, we have millions of networks connected, billions of computers. We communicate via the internet in a speed which was unimaginable when IP version 4 was designed, and we use the internet for a new type of data, for multimedia data, and it works. It works quite well, although we have to say that there are several needs for change. Several needs for change because of some fundamental problems which not can be solved by IP version 4. Let's have a look to these basic problems of IP version 4. And the biggest problem is that the number of the addresses, the IPv4 addresses, is limited. It is limited. You remember there was 32 bits long this address, so we can have maximally 2 to 32 many different IP version 4 addresses. This is about 1 billion addresses, so 1 billion, exactly 4 billion computers can be connected, can get an own IP version 4 address. It is about 1 million networks that can be interconnected by this type of protocol. So if we see the huge demand to bringing new devices, mobile devices, to bringing sensor for Internet of Things into the internet and let them communicate over the internet protocol, then we see this is a very limiting factor that IP version 4 allows only to have 2 to the 32 4 billion different IP addresses. And this is really an actual problem, since here this curve shows the number of freely available IP version 4 addresses. You see in 2012 the last the last 3 IP version 4 addresses were allocated by IANA. This was the this is the institution that's responsible for distributing and controlling the IPv4 addresses, the IP addresses. Then the last 3 IPv4 addresses are assigned by IANA to the 5 regional internet registries. These are the so-called RISE. It was done in 2011. Now these regional internet registries, few of them have freely available IPv4 address blocks, but for example, European does not have. So the RISE now only distributes their remaining blocks, and if there are new requests occurring, they cannot fulfill because of lack of IPv4 addresses. So this is the biggest problem. This is the biggest thing why IPv4 needs to be changed into a new IP protocol which provides a larger address space. But there are more problems in IPv4. In the moment one is thinking to design a successor of an IP protocol, one has also to see how to cope other problems occurring with IPv4. I already mentioned the larger number of networks that want to be connected to the internet, the huge number of mobile devices that want to be connected. And the more networks are connected to the internet, the larger are the routing tables that are needed to help the different intermediate systems to find the next hop for a data package they have to transport. So routing with increasing number of hosts become problematic. The perimeter routing tables become larger and larger. It's more difficult to find the entry. This needs time. To create and to maintain the routing table, and this needs time. In every case, a decision has to be made. What is the next hop for a data package? Another problem with IPv4 is that today we have mainly multimedia data that are communicated over the internet, and in IPv4 it is not possible to describe a service type for such multimedia data. The multimedia data, they are characterized that they are time critical. That's real time, that's videos, that's audio. And of course, this data are transported, for example, a video or a music song are transported by means of many data packages. So it needs to be clear that these data packages belong to the same data, belong to the same movie or to the same song, so that it's necessary, so that's what is needed is to have a mean to specify that such multimedia data, that these are multimedia data with special delivery requests. So the quality of service for smooth and for synchronous live transmission of video and audio data need to be specified, and in IPv4 there are no means for it. And then a third group of problems arise when we look for computer-supported cooperative work, CSCW. By means of the internet, which provides such great possibilities to let people interact which are located in different locations, then the wish and the need for software that supports such cooperative work is increasing. And of course, for such cooperation over the internet, in real time, for example, there are means needed to support such a CSCW work, so group work. And if you remember to IPv4 and all the means, we discussed in the last week, then you see there is a lack of means to support such distributed group work. So all these things, all this observation lead to the request for a new, more recent IP protocol. And it's interesting that this was already seen 20 years ago by the Internet Engineering Task Force, the IETF, which started in '94 developing a process for a new IP version. There are several reasons. This new IP version, originally it was called Internet Protocol Next Generation, IPNG. Then, when it was ready designed, it got the number IPv6. So the Internet Engineering Task Force started to work on such a successor of the IP protocol, version 3.4. And there was a question, what are useful concepts of the IP version 4 that need to be followed by IP version 6.2, and what are things to be changed? So first, the following decisions were made. There was a very successful use and of the IP version 4. So this working group, this Internet Engineering Task Force working group, decided that the connectionless character of the IP protocol should also be the basic principle for IPv6. There was another very successful concept of Internet Protocol version 4, which is used also for the successor, the Internet Protocol version 6. That is that each datagram contains a destination address, so that the data transport service allows to send different data packages that belong to the same data through different paths, so possibly different paths through the internet. Then another principle which was also used as an axiom for the development of the IP version 6 protocol was that each datagram is transmitted independently. This is a consequence of this connectionless character of the protocol. And then you remember one of the problems with IP version 4 was the increasing number of networks connected to the internet, and by this way the increasing number of hops each data packet has to take when it moves through the internet. So the design principle for IP version 6 was to look for limited number of hops to the destination. But beside of this principle that were successfully used in IP version 4 and should also be used in IP version 6, a number of improvements were done. And the first of all, there is a new address size. A new address size which overcomes the limitation of the address space of the IP protocol version 4. The new address length of the IP version 6 protocol is 128 bits, so 4 times larger than the original IP version 4 protocol. These 128 bits are grouped in 60-bit groups, and to describe these groups in an efficient way, a hexadecimal notation is used with a colon as a separator and with some means for making this address as short as possible, and one of these means is zero completion. Hexadecimal notation is similar like the decimal notation, but instead of 10, we have 16 different symbols to describe numbers. And using this hexadecimal notations, so beside of the symbols 0 to 9, we use the symbols A, B, C, D, E, F for this hexadecimal notation. So each 16-bit group can be described by one number. This is exactly the idea for the presentation of this really huge IP addresses. Then another new idea we will discuss later in more detail is that there is a new header format. There is not only one header as it was used with IP version 4, there are a basic header that needs to be used in any case, and then there are a variety of optional headers that can be used if a certain situation occurs. For example, if a data package is fragmented, then one can put all the information around this fragmentation, this administration information around fragmentation into one optional header, into such an fragmentation header. So required is one basic header, and optional are one or more additional extension headers, for example, for authentication, for encryption, for fragmentation, as I already mentioned. This is a different style of collecting administrational data that are needed to organize communication into multiple headers. And then we have different types and a new style of addresses for unicast, multicast, and clusters. And then the improvement of IP version 6 over IP version 4 is that there are a video and audio support. So real-time transmission by means of a mechanism for establishing predetermined transmission paths to meet the requirements for real-time transmission. There are more improvements of IP version 6 compared to IP version 4. The protocol is extensible. In the moment when we step from IP version 4 to IP version 6, a new protocol has to be implemented and we really have to migrate. So we will discuss this later. It's difficult to change such a protocol with a new address format. So the idea when the new IP version 6 protocol was designed was to say we have to solve the address problem forever. And when we later discuss the address format, then we will see there with 128 bits, there are so many addresses possible that we will there is no more need to think about extension. But with other things, with development of new type of data, of new type of transmission, it could be that it would be helpful to improve or to extend the new IP version 6 protocol. And here the design idea was to provide means to extend the protocol without to completely change the protocol. Then there are some new functionalities from other protocols. We will later discuss this in detail. For example, the neighbor discovery protocol, which is based on ICMP version 6 and which replaces the ARP protocol in IP version 4. There is host authentication mechanism, something like a stateless DHCP. Then there is support for multi-homing and renumeration. Multi-homing, that's for all systems that belong to different networks same time. And then, this is very important, some improvements concerning the mobility. So the mobile IP version 6, which is providing the possibility for more mobility in the internet. So in this way, the IP version 6 protocol solves some necessary problem, for example, the address extension, the address space extension, by providing longer addresses. But at the same time, also some new functionalities are included which help to improve the efficiency of the communication over the internet.